In this section, I'm going to be talking about correlation, partial correlation, and mediation effects. Drawing much of the material today from Chapter 9 of the Welkowitz textbook, which is assigned for class. This is a natural segue into regression analysis, although this particular video is going to stop at the end of mediation tests, mediation effects. So we'll start with correlation. And one way to think about correlations is that they are measures of association, which essentially tell you the degree to which one variable moves in the same direction as another variable. In other words, correlations tell you the degree to which scores on one variable coincide with scores on the other variable. And what I mean by that is that if you have, let's say, 100 people and you measure this sample of 100 people on two different variables, we don't really at this stage call them dependent or independent variables. We just call them variables. They can be anything in the world that you want to measure an association for. We take two variables and measure those two variables on all 100 people in our sample. The correlation is a measure of the degree to which variable x goes in the same direction or opposite directions, and how much, along with variable y. As variable x goes up, what happens to variable y? Does variable y go up or does it go down? And to what extent do they seem to act in synchronous patterns? If you have only a small amount of consistency between changes in variable y when you go up 1 unit in variable x, the correlation may be small. If you have a great deal of consistency in terms of the patterns that you see emerge as you go up values in variable x, and if you have a similar or consistent change either up or down in variable y, then you might have a strong correlation. If what you see as you change variable x, when you change it, if you see just sort of random fluctuations in variable y, sometimes it goes up, sometimes it goes down, then you may have a zero correlation. So that's what we're talking about here in terms of the measure of the magnitude of association. We're looking to see the rate at which the two things seem to coincide with each other in either the same direction or opposite directions. And here's a figure from our textbook from page 220. And this shows an example of a scatter plot with a correlation where you have two variables mapped out. You have the x variable, otherwise known as the x-axis. In this case, the variable down here is income in thousands of dollars, ranging from, I guess, about 15 or maybe 18,000 up to about $55,000. Presumably that's per year. And then IQ of the child. I think this is probably outdated. The textbook was published in 2011, so it certainly is outdated. But even then, the data set was probably fairly old. And this is not a real data set. This is just a hypothetical. And so what they're showing is that there's an association between income and IQ. Now, does that mean that there's a causal relationship between income and IQ? If you increase the amount of income in the family, does that mean that the IQ of the child is going to increase by itself? Or perhaps we can look at it in a different way of causality. For children of high IQ families, does that mean that IQ drives the amount of money? Either direction of causality is a possibility, but it's also possible that neither one of these has a causal relationship. Hence the very commonly heard phrase, causation is not, or correlation does not indicate causation. Causation is not shown here. Correlation cannot tell us anything about causal relationships. Now, there's some more advanced ways of dealing with correlations, primarily in structural equation modeling, which essentially attempt to ascertain a causal relationship between variables. Another way to do that, again with a correlational data set, is with a cross-like panel design where you take measures of things at different points in time for the same individuals and see how they relate. That's how Aaron and Usman, two media psychologists, have attempted to show a causal relationship of television violence on adult aggressive behavior. But at any rate, that's not our topic for today. Our topic is just how does a correlation work? How do we interpret it? So this correlation that you see, we see that there's a consistent pattern so that as values of variable x go up, so too do the values on variable y. IQ of child, I didn't know really if you can get that high. I guess maybe Einstein was about 230, but that sort of broke the broke the scale. But yeah, again, this is a hypothetical data set. It's not real, and it's not intended to be representative of any real pattern. But you get the idea here. What we're looking at is that regular increments of variable x are related to regular increments in variable y. Now, it's not perfect. In order to be perfect, the dots would have to be right on the line, and any distance from here to here is essentially error of prediction, although that's more of an issue for regression analysis. With correlation, the idea is that the closer the dots are to this line, the stronger the correlation is going to be. In fact, it has nothing to do whatsoever. It has nothing to do with the slope of the line itself. The slope of the line is merely telling you, on average, how much increase in y do you get when you go up 1 unit of x. That literally is the slope of this line of best fit. The line of best fit is this line that is the one single line that minimizes the distances from each dot to the line. I'll have more to say about that in the next video that I create, which will be on regression analysis. But for now, the key thing, the key take-home point in terms of looking at one of these scatter plots is to know that the proximity of the dots to the line is a rough indicator of the magnitude of the correlation. This would be a pretty strong correlation right here, because most of these dots are pretty close to that line. In order for it to be a weak correlation, again, the angle of the line has nothing to do with the magnitude. In order to be a weak correlation, the dots would be spread out all around this region. And moving on, here's another image from our textbook. This is a couple pages later. And this one shows a negative correlation. This one has as the variables being measured the number of years of play and the average golf score for 18 holes. I don't play golf, but I understand that you want your score to be lower. A lower score is an indicator of skill. And so the number of years would be inversely related to the number of years of practice would be inversely related to the actual score, the number of swings at the golf club that it takes to get to the finish line. Again, I don't play golf, so I don't really know anything about that. But yeah, this is a negative correlation, and again, the magnitude of this correlation is pretty strong. I can tell that by just looking at the scatter plot, because the dots on this scatter plot are pretty close to that line of best fit. Here's one from page 222 of our textbook, and this shows a zero correlation, or something very close to zero correlation, and this is the length of the big toe in inches and IQ. There should be no relationship to these, and you can see in this hypothetical that there's no clear pattern here. There's no clear indication that things are going up or down. As a footnote here, I would say that even something like this can be statistically significant if you have a extremely large sample size, because the significance of correlations is determined both in terms of the the magnitude of the correlation, but also in terms of the sample size itself. So if this correlation were extraordinarily small, it could still become significant if you had tens of thousands of data points. A researcher named Paul Meehl did exactly that in the 1960s, where he measured several thousand students in a school in the Midwest. I think it was in Minnesota, and he measured the diameter of the ring finger and their IQ and found that it was significant. Although the correlation itself was extraordinarily, is negligible, it was close to zero, but it still came out looking like it was statistically significant because of the gigantic sample size. And that's an issue related to power. Now, here's a formula for the correlation, and we call this correlation just simply R. And sometimes the longer version of the name is the Pearson product moment correlation coefficient, devised originally by Carl Pearson, although it's much older than what the formula that Pearson worked out. But Pearson worked out the formula that was subsequently adopted throughout the behavioral sciences and other fields as well. And that was, I don't know the exact date, but it was around the 1890s. And during that period of time, between 1890s and 1910, Pearson was a renowned researcher and statistician, but later advances in statistics like the F-test made Fisher look very feeble in comparison. But we still use it, and it's still called Pearson's R, so he's got his place in history. Now, there are different textbooks that, I should say it this way, different textbooks tend to have different formulas. I rarely see this particular formula in any textbook. I've seen at least a half a dozen different formulas for the calculation of Pearson R from raw data, and they all get you to the same endpoint. They all get you to the same answer. It's just different types of arithmetic substitution. But this is the one that I like to use, and there's a reason why. I think you can see how the correlation itself works pretty clearly if you use this formula. With some of the other formulas, you get to the answer and you don't really understand anything based on the calculations that you've just done. But if you do this one from scratch, if you do this formula on a data set from scratch using a calculator, you will start to develop a firmer understanding of exactly what it is that a correlation does and how to interpret it. So here's a data set, and this is fake data. It's just stuff that I made up, and I like to have numbers that don't have decimal points on them, so you can see that these ones don't. Nice, easy to work with numbers so that we can see clearly what's going on. And what the formula tells us to do in the numerator is take the sum of x minus the mean, but because we have parentheses here and the summation sign is here, what we have to do is the entire procedure all the way across before we add them up. Remember PEMDAS. Please excuse my dear Aunt Sally. So you do what's inside the parentheses first, and then you have to do what's in the other parentheses, and then you do multiplication, and then you do addition. So I left out a few different irrelevant steps, but these are the ones that are relevant for this particular formula. So what we're doing here for the numerator is we're taking x minus the mean of x, and we have our variables over here lined up for x, and here's for y. Again, these are the same people. We have 1, 2, 3, 4, 5 people. It's the same 5 people over here, and each of these 5 people are measured both on variable x as well as variable y. So we take the mean of x, which is 4, and if you can add that up in your head and see that it adds up, the averages out to 4. We take the mean of x, subtract the mean of x from each score on x. That's what this part is telling us to do. So x minus the mean. 2 minus 4 is negative 2. 3 minus 4 is negative 1, and so on. But we don't add them up. I mean, if you did add these up over here, it would add up to 0, and 0 is not useful. So that's we never do that. The only time we do that is as a basic check on our arithmetic. And we move on then to variable y. So we take variable y, subtract the mean of variable y, which is 5, and 1 minus 5 is negative 4, and so on. So we don't square them yet. You see that I've squared them in the table, but that's for the denominator of the formula, not the numerator. So just focusing on the top here. We take x minus the mean of x, negative 2, and then y minus the mean of y, negative 4, and we're going to take the product of those two. So this number multiplied by this number gives us this number. Negative 2 times negative 4. Remember that a negative times a negative is a positive. They cancel each other out. The negative signs cancel out. Negative times a negative is a positive. It gives us positive 8. Negative 2 times negative 1 is positive 2. And you can see a mismatch over here. Negative 1 times positive 3 gives us a negative 3. If you have a positive correlation, you'll be able to see that over here because the number here will be positive. If your correlation is negative, what you're going to notice is that you have a lot of mismatches of positive and negative signs. That's going to cause you to have a negative correlation. If the negatives over here outweigh the positives, then it drives the direction of the correlation into the negative range. But that's what we're doing here. That's the cross products. So we take the sum of the cross products. That's literally what this is telling us to do. Take the sum of the cross products of the deviation scores, add them up, and that adds up to 18. That goes in the top, and then in the bottom we have the sum of squares of variable x and the sum of squares for variable y. We know how to do sum of squares. We've been doing it all semester, and so you can see that I've already done that here. Sum of squares, or SS, for variable x is 26, and for variable y is 36. And again, it's just taking each score in variable x, subtracting the mean of it, and then squaring it in order to get rid of the negative signs, adding them up, and that becomes the sum of squares. So now we complete the arithmetic here, and we have a correlation coefficient. It comes out to be 0.59. We don't know yet, based on information covered, whether or not this is considered a large correlation. Correlations can go up to a positive 1. 1.00 is a perfect positive correlation, which would tell you that for every unit increase in x, you have a regular and consistent increase. It doesn't have to be 1 unit. It could be more than 1 unit. But it has to be a regular, identical increase in variable y. Every time unit x goes up, unit y would also go up the same amount. Each time y goes up, I mean, it could go up 1.4 points, but it has to go up that amount every single time you go up 1 unit on x. And a perfect negative correlation would be negative 1. So we have a range of possibility in terms of the correlations themselves. I'll have more to say about the magnitude of these correlations in a second. In fact, right here. So when evaluating a correlation, we need to keep in mind that the value that we obtain is a measure of association, of how much, for these individuals in our sample, variable x and y seem to be going along together or in opposite directions. Another way to think of this is that the correlation is a measure of the magnitude of a treatment effect. The correlation R tells us the magnitude that two variables go in the same or opposite directions. So how large is large? Here's a handy-dandy table that tells you that a correlation of 0.10, it doesn't matter if it's positive or negative. Correlation of 0.10 is small, 0.30 is medium, 0.50 is large. A correlation of negative 0.55 is larger than this one. The sign really doesn't matter. The sign simply says that they're going in the same direction or opposite directions. So a correlation R of negative 0.55 is larger than any of the three shown here that are all positive. I didn't put negatives here because it's the same. It's a mirror image. So this is a handy way to think of magnitude of correlations, but it doesn't tell the full story. Here's a scatter plot of this data set. So this, if we go back a couple slides, this variable x and y data set, what I've done here is I plotted these out so that each one of these pairs of data is observable within this graph. This particular data point right here, right in the middle, is x equals 5, y equals 4. So 5 and 4. And if we go back to the raw data, we can find that here's x equals 5 and y equals 4. So what we're doing is we're literally mapping out each one of these pairs of data. Another way to think about it is this is one person's position in terms of score on variable x and y. And this is another person's position. And this is another person's position, and so on. Now you can draw a line through here, but there's only one line that fits in the sense that it has the smallest amount of error introduced in terms of how far the data points are from the line. There's only one line that minimizes the distances the best, and that is called the line of best fit. I don't have that line in here, but when you run these in SPSS, it's pretty easy to ask SPSS to do that for you. This particular semester, we're not going to do that. In other semesters, I will. But this particular video does not have a training component for SPSS as far as correlations go. So we can see what's going on here in terms of a pattern. Yeah, there is a pattern, but it doesn't look that clear. Nevertheless, the correlation is quite large. Here's another one. This is a different data set, age, and this is from an example from a textbook, some raw data that was in a textbook that I used. You can see that there's a trend here. It's a negative correlation. I don't know the correlation R offhand, but I would say that it's probably very strong. Here's one that looks kind of close to a zero correlation. There's no real clear pattern, but in fact, and this is a different data set from yet another textbook, Stats Course Anxiety and Perceived Stats Course Difficulty rated by students. The correlation here is, we would say it's moderate to large. It's in between medium and large, where medium was 0.30 and large is 0.50. So yeah, there's a positive correlation here, but there's a lot of deviation from the imaginary line of best fit. And I'm just moving the cursor back and forth to indicate where that line would be. Maybe at some point I'll add a line to that. So it's not a zero correlation, but it's not gigantic either. And here's another example, age at September of intake and perceived stats difficulty. The age of the student does not seem to have any relationship whatsoever to perceived stats difficulty when they take a stats class. There's really no correlation. In fact, R equals 0.02. It's as close as you can get in real life to a zero correlation, showing you that as your age, when you're a student taking stats, as age increases, there's no real discernible trend here for variable y, for the perceived difficulty of the course. And some people who are very young find it very difficult. Some people who are young find it easy. Some people who are older, more in my age bracket, find it difficult, and some find it easy. So there's no real pattern here. Every time we measure a variable, we're examining the variation in the scores. And another thing that we may want to know is the variance of each of the two different variables, where the variance is the sum of squares divided by n minus 1. And this is going back to the beginning of the semester where we first encountered standard deviation. I illustrated that the computation for variance is done like this. This is the symbol for sample variance. If we had a square root sign here, it would turn into standard deviation. But such as it is, the variance of variable x is the total amount of variability attributable to variable x in squared deviation units. So this is sort of an average amount of squared deviation averaged across its degrees of freedom. Same thing over here for y, the variation of variable y. So we see that there is some variability here. There's not a whole lot. Sometimes you get variances that are really quite large, much larger than what we see here. And what we're talking about again is the variance represents the total amount of variability for a given variable. Now here what I've done is I've taken that original data set that we started out with and we have the calculation of the correlation coefficient again. And what I wanted to point out to you is that the numerator of this expression, which is the sum of the cross products, is what I call the signal, whereas the denominator of this, which is in similar to variance, it's in squared deviation units, although it's not been averaged. This is the amount of noise. So we had a certain amount of variance. Let me go back a slide. We had a certain amount of variance for variable x, which was determined by this number, the sum of squares, divided by 4, which is the number of observations minus 1. And this represents the total amount of variability in variable x and the total amount of variability in variable y. So when we look at the correlation coefficient, what we're doing is we're looking to see how much trend there is, that's the top, how much trend there is in terms of units going in the same direction or opposite directions in tandem with each other relative to the total amount of fluctuation there is inside the variables themselves, which would include both treatment effect and non-treatment effects. So this is not totally accurate. Well, actually it is. Signal plus noise. So I did get that, remembered to put that down. Some of these PowerPoints I've written many years ago. So that again, the numerator here in this ratio, it's a signal to noise ratio where the numerator in this case is just the signal. It's the amount of covariance that the two variables have that they share with each other. And the denominator is the signal plus the noise. You know, part of this is shared variance, but part of it is error variance or variance that's unique to the individual variables. And so as the signal becomes larger to the denominator, which is the signal plus the noise, then we get a larger correlation. So we want this number to be large on top, or we want this number down here to be small. We normally don't have control over these things, especially if they're naturally occurring variables. Then it's just going to be what it is, and it's not something that we can really manipulate. That's why they're not called independent variables. But if we were hoping to see a big effect on something, like a reduction in, I don't know, hostility against outgroups, you know, if we had some persuasive communication instructing people to be more accepting or tolerant for others who are not like them, then we would hope to have a negative correlation, and we would want to have a large number on top relative to the denominator. Now this is never going to be larger than the denominator because the denominator includes this part on top plus noise. That's why you cannot have a correlation that goes greater than 1. The numerator is never going to be larger than the denominator. Okay, so now returning to our table of magnitudes the benchmarks for interpreting the size of correlations, that correlation that we were working with was pretty large. It was 0.59. But keep in mind, and this is something I want to caution you about, keep in mind that small correlations can be very important, and that statistical significance doesn't really tell us the thing that we want to know. The thing that we want to know is whether or not the correlation is important. And if you have a treatment, let's say, that increases the level of tolerance that people have for those who are not like them, then even a small correlation can be something that has large practical importance. We would expect that a small correlation like that would be consistent then with, and perhaps causally related to, a reduction in hate crimes. Let me use a different example, though, shift out of that area and use one from biomedicine. The Framingham Physicians' Heart Study was an ongoing, it's still going on actually, but it was an ongoing study that was active in Framingham, Massachusetts from the 1970s into the 80s, and they stopped it at one point, at least one part of the study, where they found that taking aspirin reduced the mortality risk of heart attacks. The effect, I won't go through the calculation of the effect size there, but the effect expressed in terms of a correlation R was 0.034. It was a very, very small effect, but it was positive, and what it meant was that for those who were taking baby aspirins, they had a very slight but real increase in chance of survival of getting through a heart attack. And, so when you have something like that, even though it's just a small effect, only a few people may be saved, but if you're one of the people who lives instead of dies, then you're quite happy about that, at least presumably. So that's, that can be something where a small effect can have a very large clinical significance. So I don't want you to get caught up in these labels here. This is a benchmark for socio-behavioral research, where attitude research tends to be between these ranges of 0.3 to 0.1. And if you ever get anything as large as this in attitude research, it's pretty big. In biomedical research, often we're dealing with effects that are very small, and that's the reason why in biomedical research they tend to do studies with thousands and thousands of people, because they want to locate even those effects that are very small, because they have the possibility of saving a few lives. Okay, so here's some additional issues with correlations that you should be aware of. And this figure is from our textbook, from the Welkowitz textbook at page 238. It shows a curvilinear relationship, so that as x increases, at first you have an increase in variable y, but then variable y starts to drop down again. And what happens if you do a correlation on a data set like this, even though we see that there's a perfect relationship, but the relationship is nonlinear, what happens is that the correlation will in fact tell us that this is a zero correlation. The Pearson product moment correlation coefficient cannot detect curvilinear relationships. It's set up to only detect linear relationships, and that's why it's such a sort of a simplistic way of looking at data, because it's like a hammer. There's only so many things you can do with a hammer, and if you try to use a hammer to do something that needs a tool with more finesse, you're just going to mess it up. And so that's why correlational studies, sometimes people say, well, it's just merely a correlational study, it's not very impressive. Although there's sometimes things, and I'll have an example of this later, there's sometimes studies that use correlational data sets that can be quite impressive. But if you have a nonlinear relationship, the correlation is going to underestimate that relationship. And that's described in the textbook. Another assumption of correlations, this was an assumption. So one of the assumptions of correlations is that the data are linearly related to each other, that the variables themselves are linearly related to each other. Another assumption of correlations, which is not discussed in our textbook, is the assumption of homoscedasticity. You can see the spelling there, kind of a hard word to say. I've had practice at it, homoscedasticity. And what it means is simply similar variance. Similar variance. I don't know what the root here is for skedasticity, but it's the same thing as variance. And if you have a situation where you have heteroskedasticity, what you're saying is that you have different levels of variance at different stages. And this is a figure that I just pulled off of the internet from an article that seems to have not been published, but it was exactly what I was looking for, where you have variable x going up and variable y, but there's a smaller amount of variance here. And I guess what we're looking at here would be the fact that people who have very low income need that money. They don't have any savings, and so you have very narrow ranges here. There's very little variance. So what we're talking about is that the variance, let's say at 2500, the variance would be represented by this range going up and down in variable y. That's the variance at this level of x. Whereas over here at higher levels of income, we see that the variance increases. The variance becomes very wide, and that would be a situation where you have heteroskedastic data. Heteroskedasticity is not a good thing. It means that well, you're in violation of one of the assumptions of the correlation coefficient. The textbook does not mention anything about this, but it's an important assumption. So the first assumption was that the variables are linearly related to each other, and the second assumption is that the data is homoskedastic, that you do not violate this assumption with heteroskedasticity. And so here you have the assumptions. The textbook said that there's only really one, that it's linearly related, but we can add these other ones too. A lot of other textbooks do. So homoskedasticity is the second one. And then the third assumption of correlations is that you're dealing with interval data or continuous data of some type. But I wrote here, but see also Kendall's tau. That's Greek letter tau. I tried to use a font that made it look like a tau instead of a T, but I couldn't find any. This is Arial, and I shifted to Times New Roman, but that didn't help either. That's tau, T-A-U. And that is a correlation for non-parametric data, for ranked data. So there are ways to deal with this violation if you are in violation of it. It works pretty much the same. And then the fourth assumption is that you have a smaller, you have little skew, or a small amount of skew, and a few outliers. In other words, that the data should be normally distributed. If you have highly skewed data, you're going to get some weird correlation because of it. You can have an overestimate or an underestimate of the magnitude of relationship between the variables. Here's an example from our textbook at page 234, where you have the same data set that we had when we started this presentation, but they added another variable down here, and they never reported what the original correlation was, but it looked like it was about 0.7 or something like that if you don't have this data point. But adding this data point in as an outlier, an artificially low score at a high level of x, takes your correlation down. And so the effect of an outlier, depending on whether the outlier is down here or up here, is that it's going to either increase or decrease the, actually out here, or let's say right down here, can decrease, as this one would, or if it was over here, increase the magnitude of the correlation. So outliers really play havoc with the correlation calculation itself. Here's yet another thing, and this one is discussed in the textbook, another issue that pops up sometimes, and this is called range restriction. This occurs when the correlation is based on only part of the data set, and so in this hypothetical, what they've done is they've used test scores, variable x, and grade as variable y. Now we might be talking about something like the admissions test score or some other form of standardized test here, SAT or GRE. If you're only looking at people in this narrow range, it may look like the correlation is close to zero, but in fact if we had all of the data points, we'd find that the correlation coefficient is strong and positive. That's what happens when you have range restriction. Oftentimes, basing your correlation on a restricted region of the data set reduces the correlation coefficient itself. It makes it smaller, closer to zero. It doesn't necessarily put it into the negative zone, but it brings it closer to zero. So I wanted to find some examples of this that go beyond what's in our textbook, and I have a copy at home. Most of my textbooks are locked up at school, and here in the COVID-19 pandemic, we don't have access to the school, so I can't get any of my books. But I have this old one, Michael Furr's excellent book, although this is an older edition of his book on psychometrics, and he provides an example of range restriction using the SAT, Scholastic Aptitude Test, with the older scoring system before they changed the scoring, where you have two different sections where you can have a range up to 800 on each one. So the combined math and verbal, you can get up to 1600. Now over here you have GPA, and this presumably is first year GPA when you enter college. Well, I thought GPA went from 1 to 4. What he's doing here is he's arranging the data. This is fake data, but it actually resembles pretty closely real data sets on standardized tests in first year GPA. I've seen them and they look quite a bit like this. He's extending the data set down to where it naturally would be, although physically in real life and in reality it's not possible to have a negative GPA. The lowest you can get is 0. And I think really in most schools the lowest you can get is would probably be somewhere around here, because you get removed from college if your scores get too low. And the same thing up here, the range is extending further up on the y-axis than you would normally get, because most of the time your GPA can range from 0 to 4, where a 4 would be an A. A 4.0 would be a perfect A average. Although there are some exceptions. There's some schools that do provide that students can excel beyond that by some extent. But at any rate, the correlation here for this fake data set is R equals 0.605. It's a strong correlation. Now what happens if you get rid of the extension below and the extension above? What happens if we chop that off? Here's, and this is all from Michael Furr's text on psychometrics. This is an example he put together. Shaving off that bottom part that's not real, or not based in reality in terms of actual test scores, and shaving off the top part really has no effect on the correlation coefficient. It goes down very, very slightly to R equals 0.603, from 0.605 to 0.603. But now look at the third of these three figures. If we restrict the range so that we're only going from 900 and above, the correlation drops substantially down from 0.603 to 0.474. And this is it's it's not that it's a bad way of looking at the data, but what happens is that you're underestimating the trend because you're not getting access to these people. Well, why would it be that we don't get access to these people? Well, for people who, if we're gathering data based on, let's say, prestigious universities, uh, people with scores down here are not going to get in because the prestigious universities have cutoff scores that's where they say we're not going to take anybody with a SAT or a GRE that's down here. Um, one way to think about that too, though, is that it's their loss because if you're only looking at the standardized test score, you're not looking at the whole package of information that you have at your disposal about the applicant to college. And so when I do this sort of stuff, I like to look at not only the GRE test scores, but also the letter of recommendations that the applicant has from faculty at their previous institutions. And also I look at their scores on their different classes and see if there's anything that stands out in terms of areas of strengths as well as weaknesses. And then I also look at what are the possible explanations for the time that they weren't doing so well in college. And maybe that has something to do with a life difficulty that they've overcome and now they're doing better. And I look at samples of writing and so on. But you get the idea. If you're just looking at the standardized test score, you're not seeing the whole picture. But that's what's going on here. So data sets are often cut off like this, or you have limited access to information down here because people didn't go to college at all. So the correlations that we get from a restricted range, they underestimate what we would have if we had the full data set like this. And yes, standardized test scores do a decent job of predicting first-year GPA. It doesn't give a perfect prediction, but it gives a decent prediction. But again, I like to combine it with other predictors as well. Now, there's a lot that can be said about standardized testing, and there's some really nice books on the topic that are available. I've read a couple of them about the various different strengths and weaknesses of standardized tests. But one of the curious things that I've noticed is that critics of standardized testing often refer to range restriction inaccurately, saying that the restricted range causes an overestimate of the magnitude of the effect. They're wrong. It actually causes an underestimate of the magnitude of the effect. So that's range restriction, and that's the kind of thing that would fit well into a multiple choice question. Hint, hint, hint. And that is covered in the textbook. It's covered with this example right here, figure 9.6. I don't recall what page that is. It's in chapter 9. Okay, so now shifting gears just a little bit, talking about John Venn and his Venn diagrams. Venn was a British philosopher who was he dabbled in mathematics, and he's best known today for his Venn diagrams. And I think the Venn diagram is very useful in order to explain my next topic in terms of how we think about correlations. So what we have here are two circles. This represents, the red circle represents all the variance on variable x, and the blue circle represents all the variance on variable y. In this example here, this visual example, there's no overlap. That would be a representation of something where we have a zero correlation. So in this example, we have two variables measured separately. They're referred to as x and y, I thought I took all my animations out. The animation sometimes makes my screen capture program crash. So So I'm referencing here the sum of squares. That's what we're talking about here in terms of the variance of variable y and the variance of variable x. It's the sum of x minus the mean of x squared divided by n minus 1. So in this example, r equals 0.0. You know, those animations are where they shouldn't be. Okay, so now here, this is where we get into the interesting part. In this hypothetical arrangement, this visual hypothetical, let's say we have a modest amount of correlation between these two variables, x and y. Let's say the correlation was r equals 0.23, positive correlation of 0.23. One way to think about this is that the amount of variance that's shared is determinable by taking r and squaring it. So if we take the overlap area here as a visual representation of shared variance, we can actually find the exact amount of shared variance by taking r and squaring it. So r squared equals 0.0529. I was trying to get as close as I could to 5% because we all have a pretty good understanding of how small this is. Just a little bit of shared variance. And I tried to make these graphically represent about 5%. So that would be between a small and medium effect. There's a little bit of overlap between the variables, but not much, and we have no idea if it's causally related. Here's a situation where you have a large effect, r equals 0.7, but even with a large effect, we see that the amount of shared variance is only about 50%. In fact, it becomes 0.49. 0.7 squared is 0.49. So about half of the variance is shared between the two variables. The amount of overlap represents the amount of shared variance that one variable has with the other. Here we have nearly perfect correlation of 0.97, and you can see that after you square it, it still has a very, very large amount of shared variance, 94%. And this one is perfectly correlated. It has variable x, the red circle, is completely overlapped with variable y, the blue circle. So if you know anything about the responses on variable x, then you also know the person's responses on variable y without measuring them. That's what a perfect correlation tells us. Now, what if you have three different variables? And the illustration that I like to use is ice cream sales and riots. Ice cream sales, the red variable, can be thought to be moderately correlated with riots, the blue variable. But as you can see, there's a third variable here, which is probably the causal variable, and that's temperature. As temperature goes up, you have more ice cream sales, and as temperature goes up, there are more people outside, which is what you need in order to have a riot to happen in the first place. You can't have a riot if everybody's stuck at home. So during the coronavirus pandemic, I would predict very, very few riots worldwide. Except if, you know, they're battling the police or something, I don't know, because they don't want to be locked up. So, you know, this begs a question: how much of the potential causal relationship is left over between ice cream sales and riots? You know, if we didn't have the measure of temperature, if we just had ice cream and riots, there's a fairly high amount of shared variance between these two different variables. And you know, one possible causal relationship is that if you eat your ice cream too fast, it gives you the brain freeze and you start rioting. Or you can have the reverse direction of causality, that after rioting all night long, you want to cool off with some ice cream, which is, of course, preposterous because everybody knows after rioting you want to drink some beer. And the beer can also make you riot more, I don't know. In the riot that I was in, and I like to talk about this one in class, but in 1988 in New York City, I was in the Tompkins Square Park riot, where hundreds really thousands of protesters uh, engaged with the police. The police were beating people up left and right. It was just a terrible thing. It is amazing for me to watch. I watched it all night long from 11 p.m. until about 4 in the morning. Over 50 people got sent to the hospital that night, but none of them were eating ice cream. And it was summer, and that's the thing, is that there are more people outside, and so in that particular riot, the vast majority of people who were there were just there watching what was going on, like me. I wasn't a rioter, I was just watching. And then the police freaked out and called up hundreds of other cops to come and beat everyone up. It was just insane. There's video footage of it if you look online, but it's not very good quality. Anyway, so what we want to do is we want to take this and we want to take out temperature. We want to remove that from the equation so that what we're left over is just the shared variance between ice cream sales and riots. And what I've done here graphically is I've removed this whole section for temperature. And now we can see that there's only this tiniest sliver, maybe 1/2 of 1%, or I don't know, maybe up to 1%, of shared variance between ice cream sales and riots. And what I've done here is essentially what's known as a partial correlation. This would be the partial correlation of x and y after controlling for z, variable z, in this case temperature. So I want to spend a few minutes talking about shared variance, or rather partial correlation, and how it relates to shared variance. So now, we've got 3 different variables. Each of these variables has a simple correlation, where the simple correlation is just the straightforward Pearson correlation between x and y, or between x and z, or between z and y. So if you have 3 variables, there are 3 possible combinations of simple correlations of 2 different variables with each other. That exhausts all the possibilities. Here's the formula for a partial correlation. I've done this using a calculator. It's kind of challenging, but it can be done. And what we're doing here is we're looking at the correlation of x and y after taking z out of it. That's what this symbol here represents, after controlling for z. And you have to go through these steps to take all 3 of the different versions of correlations, the x-y correlation, the x-y correlation times the y-z correlation, and down here the x-z correlation and the y-z correlation again. What that's going to do, and I'm not going to focus on the calculations themselves because they're really kind of tough to do. But the whole purpose of this is to get the amount of shared variance between these 2 after removing the 3rd variable from it. And so here's a real-life example. Actual publication, Linda Williams published an article in 1994, which was it was based on her dissertation work in the 70s, where she had found hospital information about children who had been referred to examination because of child abuse. And she had the identities of these individuals. All of this was reviewed by IRB and approved. So her original dissertation was based on the abused children at the time that they were abused, but I don't know, 20 years later or something like that, she looked up as many as she could find, both males and females, although this original article, this one here, is only the females. And she asked them a question about whether they remembered ever having gone to the hospital because of, well, for anything. She couldn't say because of child abuse, because that would trigger the thing that they wanted to measure, whether the person had memory of the event. So the people who were working for her research team fanned out and found as many of these individuals as they could without telling them what they were looking for. They said, was there ever a time when you were a child that you had to be taken to the hospital? And So she presented a table of correlations like this. I've reformatted it somewhat. The study was a really hot paper when it was published because it was the biggest and the best paper at that time on the topic of recovered memories of child abuse. And what she was finding was that there were quite a few, in fact 38% of the adult women failed to disclose that they had been taken to the hospital as a kid because of child abuse. Now then there was a whole debate about whether the 38% represented inability to recall as opposed to a refusal to tell the investigator, because they didn't want to talk about it. Or whether the lack of recall was because the memory had been repressed or merely forgotten, etc. But that's not what I want to focus on here. What I want to focus on is the use of force in perpetration of the sexual abuse at the original event, the age of the child at the original event, and whether the child whether the adult had lack of recall. So this is dichotomously coded. Age, of course, is age, and I think this force was a 4-point scale. And she represented the correlations with these, extra decimal points that were not needed. So we've got these 3 different correlations. And for a partial correlation, this is all you need in order to partial out the contribution of the confounding variable, which I think the confounding variable here is age, and see what the force and lack of recall relationship is after taking age out. So what it looks like here is that there's a relationship between lack of recall and force. And so it's a negative relationship, negative correlation. As force goes up, lack of recall goes down. What does that mean? As force goes up, lack of recall goes down. In other words, recall goes up. So there's a positive correlation between force and memory of the event, or disclosing of the memory of the event. But you see there's a double negative here. It makes it hard to read. But this is how she presented it. So force is negatively associated with lack of recall. She actually mistakenly described it in the text of the paper to say that there was an association between them that was positive, that force was related to lack of recall. So here, what I've done is I've taken the 3 different simple correlations, the 3 different simple correlations between these variables, and I plugged them into my partial correlation formula, because what I want to control for is z, which is down here. This is z, the confounding variable. And the reason why I think it's a confounding variable is because younger children are not going to remember because they're young, and also because, and we can see it over here, force is used more frequently with older kids. So higher level of force is a positive, stronger number on this measure of force. It was 1, 2, 3, or 4, or maybe 0, 1, 2, 3. I don't remember. But higher levels of force represented actual higher levels of force being used in perpetration of the event, of the crime. And so we have a positive relationship between age and force, and that needs to be ruled out from the lack of recall and force relationship, because more force is going to be used with older kids, and older kids have better memory. So in order to partial out the z variable, age, we plug all these in, and what's left over after controlling for age is almost nothing. So there's, in terms of explaining what we're looking at here, this number drops down to virtually nothing after we control for age. So the lack of recall to force relationship disappears after controlling for age. Now, I haven't kept up with the literature in this area, so I don't know if there are other studies that also looked at similar layout of variables and what they found. But at least in this particular study, there's no evidence whatsoever that force was equitable with inability to recall the event of child sexual abuse. Now, so that's partial correlation. And it's very useful. One of the reasons why it's very useful is that you can plug there are calculators online that can do this for you very easily. You can take any simple correlations that you want and partial out a third variable. So you can do that on other people's published data, which is actually a really cool thing to do, which is what I did here. So the next topic, and this is the last one for this video, is mediation effects. This analysis is used from the following source, Barron and Kenny. Their article on mediation effects in research is one of the most heavily cited articles in all of psychology, I think. It's been cited thousands of times, and many people use this approach. And so what we're talking about here is an indirect pathway of influence. When you have three correlated variables, it's possible that one variable acts as a causal agent on a second variable, and that the second variable then in turn influences a third variable, thus creating an indirect path of causal relationships. So as my example, and I got this from a different textbook, a textbook on multivariate analysis of data, research has shown that there's a correlation between income and health behaviors, such that, for example, prophylactic health behaviors like breast self-exam to detect cancer is one that has a correlation between income and that behavior. That is to say, women from families with more income, with higher levels of income, are more likely to engage in regular breast self-exam in order to detect cancer. And detection of cancer is it's really critically important, and this is a very simple technique that can be done to detect early onset, the lumps that might be an indication of breast cancer. And it's definitely something to take seriously as you get older. I had a friend once. She was 29 years old when she died of breast cancer. It was kind of an outlier in terms of the lower end of the age bracket where people would be at risk. And it was such an unusual medical case that she was featured on the cover of, I think, Newsweek magazine. I can't remember if it was Newsweek or Time. It's just a tragedy. She was my next door neighbor, and just a lovely person, and she died from that. It had advanced to the point where it couldn't be treated by the time she found it. Because as someone who was that young, she wasn't doing regular breast self-exams. The guidance is to do it later in life, but it's certainly important to do. So let's take this hypothetical to an absurd level. If a woman wins a lottery and instantly becomes rich, will she suddenly increase the amount of breast self-exams? No, that's absurd, because there's no causal pathway there. It's an indirect path. The path toward health behaviors is not a direct one. Instead, higher income is correlated with higher levels of education, and it's then the education that leads to greater health behaviors. So having a graph will help this make sense. Here it is graphed out. And so we have these three possible correlations. The income and education correlation is going to be strongly positive. Education and health behaviors is moderately positive. And then the income and health behaviors. This is where we want to know whether this is a direct path or whether it's a mediated path. And I lined this up to be consistent with Barron and Kenny's structure of what they argue for. In order to show a mediation effect, you have to have a significant correlation here, here, and here, and when you have them all three together, when you partial this, when you control for education, this one has to drop out of significance. Because really what's going on is that income is leading to higher education, income of the starting family leading to higher education of the children growing up in that family. And then the education is what leads to the health behaviors, not the income. So, according to Barron and Kenny's model for mediation effects, and this is the source of many great multiple choice questions that are very confusing. In order for something to be considered a mediator, in this case it would be education in our example, these three conditions must be met. Path A must have a significant correlation showing that they share variance between these two. Path B must have a significant correlation. A mediator can't mediate something if it's not related to the outcome. So this has to be significant, showing that they share variance. And then the third one is that path C must be significant when you measure the simple correlations, and it must become non-significant when the paths A and B are controlled. In other words, if we partial this one out, like we did with the partial correlation of ice cream sales rights and temperature, if we partial this out, what happens to this? If this pathway becomes non-significant, then it's a sign that we have a true mediator effect going on. So I'm going to do this with the example used with income, education, and breast self-exam. Oh, actually, this is from a different. This is from a stats textbook, different example. Maternal care, self-esteem, and self-efficacy of the child. We see that the simple correlations here are all significant. They have to be in order to fit into Barron and Kenny's model of mediator effects. So the hypothesis here is that maternal care causes children in that family to have higher self-esteem, and then higher self-esteem has a causal relationship in terms of a greater sense of self-efficacy. But maternal care doesn't cause self-efficacy by itself. It has to go through this route in order to do it. That's what a mediator is. So we see that the three correlations, the simple correlations, are all significant. And if self-esteem is the mediator, then the pathway on the bottom is going to drop out of significance when we control for self-esteem. And normally the way to do this is with structural equation modeling, in which case you'd have also a value here. When I did this, I did not have structural equation modeling set up in SPSS, so I had to do it with just the basic regression model, which doesn't give me this path. I'd have to have Amos to do that. Analysis of, what is it called? Analysis of moment structures, program for structural equation modeling. It's a plugin that's used in addition to SPSS. So what we see here is that the simple correlations are here, and the bottom one drops out of significance when we're controlling for self-esteem. This pathway stays significant, indicating that this is still related to self-efficacy, but this one drops out. So it's evidence that this is a mediator effect. Here's a real example of an article using mediator effects. I use this one in my research methods class sometimes and have people read it, but in this case we'll just look at the graphics. The researchers here were interested in correlated data, and they wanted to see whether or not suicidality and criminal behavior are mediated pathways, such that child abuse causes other things internalizing and externalizing behavior, and then it's the internalizing and externalizing behavior that lead to suicidality and criminality. So child abuse has an indirect pathway to those outcomes. I just did a screenshot of their hypotheses, and so it says here the present study has two aims, one theoretical and one practical. I'm only going to do the theoretical part. Our primary interest lies in whether internalizing and externalizing psychopathology mediate the relationship between abuse and lifetime instances of suicide-related behavior, that's SRB, and criminal behavior using Barron and Kenny's 1986 conditions for testing mediation. We predict that A, abuse will relate to externalizing, internalizing psychopathology on the one hand, and both SRB and criminal behavior on the other. That's the simple correlations. And B, externalizing will mediate the relationship between abuse and criminal behavior, and internalizing and externalizing both will mediate the relationship between abuse and suicide-related behavior. So A, this first one is just that they're going to have simple correlations that are significant. B is that you have a one-sided mediation effect, that externalizing behaviors like drug abuse and psychopathy will mediate the relationship between abuse and criminal behavior, whereas C, internalizing and externalizing psychopathology will both be mediating factors between child abuse and suicide-related behavior. Not going to talk about the methods here. The methods are interesting, but it's, for a different class. Here's the outcome, and you see the mediation model up here. Here's the origin, and what they're doing is they're positing or hypothesizing a relationship between abuse and externalizing psychopathology, as well as internalizing psychopathology. And you can see that there is a significant simple correlation here. These are all the different types of abuse combined into one scale. And up here we have drug and alcohol abuse that are by themselves correlated with each other, as well as antisocial behavior as judged by a psychopathy checklist. And down here you've got depression, anxiety. That's for the internalizing behaviors. So abuse is moderately related to both of these. And in a previous table they showed all the correlations and they were all significant. But what we see here is that this pathway, this direct pathway between abuse and lifetime suicide-related behavior is no longer significant. It is 0.06. Well, it's darn close to being significant, but it drops out. In the simple correlations, it was much larger than this. So it's, somewhat weak evidence of a mediator effect. I think if this had gone to, real high p-value to be really non-significant, it would be stronger evidence of a mediation effect. But it's pretty good, and I like the model. I really like the paper, the study that they did in the analysis, and you can see that yes, it seems that abuse is related to externalizing, and that these in turn have a moderate relationship to lifetime suicidality. And same thing down here. Well, actually, when we go to abuse to internalizing, it stops. Internalizing does not lead to lifetime SRB. It's kind of an interesting finding, and that's contrary to what they predicted. And then the next one, we have the lifetime criminality, and lifetime criminality, you can see, is significant in the top path for externalizing, and we would expect that to be so because of the psychopathy here, the antisocial behavior. But it's interesting that child abuse stays significant here, although it's about it's the same magnitude as the previous slide, but it's more highly significant. So it's a small to moderate correlation. But you get the idea here. So what we're looking for is indirect pathways, and there seems to be some evidence of indirect pathways of child abuse being routed through these other behaviors, and that those other behaviors in turn are causally related to suicide-related behavior and lifetime criminality. So with all of that, we can stop. I think this is definitely a good place to stop, and we've covered a lot. It's the various different aspects of correlation, as well as the partial correlation, and you saw how in the Venn diagrams we can visualize the shared variance of the variables with each other, both the simple correlations and after controlling for a third variable. And then here, which is the Um Really, the most advanced way to use correlations with a structural equation model, and the most elegant, I think, way to use them in terms of looking for causal pathways through third variables. So we're not just removing variables from the analysis, we're looking to see how one variable indirectly relates to an outcome through another variable, and that's the mediation effect. Okay, well, I think that's good. I will talk to you again in the next presentation on regression analysis.